Today, here in Mechanics of Deformable Bodies, we are now going to proceed to our fifth lesson. This will be about shear and moment in beams. And this will be the first part of our discussion. And for this discussion, students must be able to demonstrate knowledge and understanding of types of beam and beam loading. And students must be able to demonstrate knowledge and understanding of shear and moment equation in diagram. Before we talk about the shear and moment in beams, let us first define what is a beam. Members that are slender and support loadings that are applied perpendicular to their longitudinal axis are called beams. Okay, so let's say this is the axis of the beam. Okay, class, the loadings that this support are loadings that are applied perpendicular to the axis. Okay, so class, in beams, no, the loadings here, class, no, it's not applied in the axis, okay, of the beam. So it's not applied actually. Okay, so again, the loads here, class, are applied perpendicular, okay, to the longitudinal axis of this beam. Okay, so beams are considered among the most important of all structural elements. Okay, so class beams in general, they are long straight bars having a constant cross-sectional area. Okay, and class beams, they are used to support the floor of a building, no, as shown in this figure. Okay, so class, let's say the flooring here. Okay, so the flooring here, class, it will be supported by these beams. Okay, so these girders actually are also beams, no? Okay, and also class, no, for bridges. Okay, so let's say for the deck of bridges, okay, so they are supported class, no, by these beams. Okay, and also class for wings of an aircraft, no, so there are also beams, no, here, or there are elements here, no, in these wings that serve as a beam. Okay, and also class for automobile, okay, so its axle, okay, so they act as a beam. And also for cranes, so this is a crane class, no, and this is the boom of a crane. Okay, and this boom of a crane, this also serves as a beam. Okay, and also class, actually the bones in our body, in a human body, they actually act also as a beam. Okay. Okay, so class, here in our discussion, we are going to analyze the internal forces, okay, and moment that act on a section of a beam. Class, remember that if we are going to cut a transverse section, okay, in a beam, okay, so we will see internal forces and moment acting on that section, right? So, class, these internal forces give rise to two kinds of stresses on a transverse section of a beam. Okay, so the first one will be the bending or flexural stress that is caused by the bending moment. And the second one will be the shear stress due to the shear force. Okay, so class, this discussion, this is concerned with the variations of the shear force and the bending moment under various combinations of loads and types of supports. Okay, so knowing the distribution of the shear force and the bending moment in a beam is essential for the computation of stresses and deformations. And later on, it will be used class, no, in designs, no, in designs of beams. Okay, so let's discuss now the different types of beams and beam loading. So we will start with the types of beams. Okay, so class, beams are classified according to their supports. Okay, so the first type of beam class is what we call simply supported beam. Okay, so simply supported beam, these are beams that have a pin support at one end and a roller at the other end. So this is an example of a simply supported beam. As you can see here, class, this beam, no, so at one end, this is supported by a hinge or a pin. Okay, and at the other end, class, it is supported by a roller. Okay, so class, the pin support prevents displacement of the end of the beam but not its rotation. class, as we know, for hinges or pin supports, no, there is no moment reaction, right? No, so class, if there's no moment reaction, meaning to say the beam, it will have the freedom to rotate since it's not restrained, or it doesn't restrain moments. Okay, so meaning to say it will have the freedom, okay, to rotate. Okay, anyway, so class, the second type of beam is what we call cantilever beam. So cantilever beam built into a rigid support at one end with the other end being free. Okay, so class, this is an example of a cantilever beam. So class, this cantilever beam, okay, so at this end, this is free. Okay, and at the other end, class, this is fixed supported. Okay, so this is fixed supported here, class. Okay, and the built-in support prevents displacement as well as rotations of the end of the beam. Built-in support or fixed support, ha? Okay, so class, as we know, no, for fixed supports, there will be a moment reaction, right? So meaning to say, since there is a moment reaction, so the support class now will restrain, okay, the beam, okay, to rotate. Okay, so that will be the second type of beams. And then the third type, class, is what we call overhanging beam. So overhanging beam, they are supported by a pin and a roller support with one or both ends of the beam extending beyond the supports. So this is an example, class, of an overhanging beam. So in this case, class, no, both ends of the beam have extension beyond the support, right? So there's an overhanging here, and there's also an overhang here. Okay, so class, also for beams that only has extension beyond the one support. Okay, so let's say the extension is only here. At the other end, there's no extension. So that's still considered as an overhanging beam, ha? Okay, so class, these three types of beams, they are statically indeterminate. Meaning, class, no, we can solve the support reactions here, class, no, using the equilibrium equations that we learn from statics of rigid bodies or engineering mechanics. Okay, so they are called statically indeterminate because the support reactions can be found from the equilibrium equations. Also, class, the beams as shown in this figure, class, so these are other types of beams. Okay, so these beams, class, no, they are called statically indeterminate beams. Okay, so these beams are over-supported in the sense that each beam has at least one or more reaction that is necessary for support. Such beams are statically indeterminate. The presence of these redundant supports requires the use of additional equations obtained by considering the deformation of the beam. As you can see here, class, no, let's say for this beam, so this is called prop cantilever beam. So this is fixed supported at one end, and at the other end, class, this is supported by a roller or a hinge. No, so class, this is statically indeterminate because here, class, the equilibrium equations, it will not be enough, no, to solve for these reaction forces and reaction moment. Okay, so same here, class, no, with this type of beam. So this type of beam, class, no, so this is called fixed or restrained beam. Okay, so this is fixed supported at both ends. Okay, so again, class, the reaction forces here and moments, class, no, the equations from equilibrium, class, it will not be enough, okay, to solve these reaction forces. So also, class, we have here what we call continuous beam. Okay, so this continuous beam, class, obviously, no, so this is also statically indeterminate beams. Okay, so class, the analysis of statically indeterminate beams, it will be discussed in your succeeding courses. Okay, so for the shear moment equations and shear moment diagrams, class, the determination of the internal force system acting at a given section of a beam is straightforward. we draw a free body diagram that exposes these forces and then compute the forces using the equilibrium equations. Okay, so however, class, the goal of beam analysis is more involved. We want to determine the shear force V and the bending moment M at every cross-section of the beam. Okay, so to accomplish that, we must derive the expressions or equations or functions for B and M in terms of distance x measured along the beam. Okay, so this, again class, these expressions, equations, or functions, it can be derived, okay, from the equilibrium equation for shear and for moment. Okay, and also class, by plotting these expressions, equations, or functions, no, to scale, we obtain the shear force and bending moment diagrams for the beam. Okay, so the shear force and bending moment diagrams, they are convenient visual references to the internal forces in a beam. In particular, they identify the maximum values of V or shear and moment. Okay, so these maximum values class, this will be used kasi no, in design of beams. Okay, so this is really an important topic no, that we know how to derive the shear moment equation and how to draw, okay, or plot the shear moment diagrams. Okay, so before presenting a method for determining the shear and moment as functions of x and later plotting these functions in the shear and moment diagrams, it is first necessary to establish a sign convention so as to define positive and negative values for shear and moment. Okay, so although the choice of a sign convention is arbitrary, here class, we will use the one often used in engineering practice and shown in this figure. Okay, so the positive directions here class will be as follows. So for loadings class, for loadings that act upward on the beam, they will be assumed as positive, ha? Okay, as shown here. So these are upward loadings. Okay, so this will be assumed as positive. Okay, so also class for shear force. Okay, so we will assume positive internal shear force if it causes a clockwise rotation of the beam segment on which it acts. Okay, so let's say for this beam segment, okay, so at this section, let's say the internal shear force is this internal shear force. So as you can see here, class, this internal shear force, this will cause a clockwise rotation, right, of this beam segment. So this shear force, it will rotate this way. Okay, so this rotation class, no, so this is actually clockwise. No, and also for this internal shear force, for this beam segment class, so it will also cause, no, a clockwise rotation here. Okay, so it will rotate this way. So this is also clockwise. So that's our assumption have for positive internal shear force. They will cause a clockwise rotation on the beam segment. Okay, and also class for moments. Okay, so the internal moment that tends to bend the beam element concave upward. Okay, so let's say for this beam segment class, now at this section, this is the internal moment. So class, this internal moment, so this is like this, no, or like this. And so for this, okay, so let's say it will rotate, no, the beam, no, this way. So if it rotates the beam this way, class, okay, so what happens is that this beam, okay, it will bend this way. It will be bent this way, no? If the moment is this way, so the beam will bend this way. So class, this bending, okay, so this is actually concave upward, right? If the moment is applied this way, or the internal loading is directed this way, so it will be bent. It will bend the beam concave upward. Okay, so that's the ano class assumption for positive moment. Also class here for this internal moment. Okay, so for this internal moment at the section of this beam segment, so this will also, since the moment is directed this way, so this will also bend, no, the beam segment this way. So this will be bent concave upward. So this is actually easy class to remember, no? So it will be a positive moment class if the bending, okay, of the beam is like it's ano, no, it's a smile, right? So it's smiling. Okay, on the other hand, class kasi, no, if we are going to let's say the internal moments are directed oppositely. Okay, so what happens is that if the moment is this way, applied this way, so what happens is that the beam will bend concave downward, right? So that will be ano, no, that will be sad. It will be as like a sad sad beam, no? So since this is concave downward, okay, so this will be negative. And also for this, no, if this is directed oppositely nga, no, so this will be directed this way. The moment will be directed this way. Okay, so this will bend the beam this way also. Okay, that will be concave downward, and it's ano, no, it's sad. So that will be negative moment. Okay. So class, loadings that are opposite to this are considered negative. Okay. Okay, so the shear and moment diagrams for a beam can be constructed using the following procedure. Okay, so the first step, class, no, will be you have to solve first, okay, for the reaction forces or moments, okay, in the support. Okay, so we can compute those support reactions and moments, okay, from the free body diagram of the entire structure. Okay, and after that, class, no, we can now establish, no, the shear and moment functions or equations. So for establishing the shear and moment functions and equations or equations, no, so this will be the step. So the first one, we have to divide the beam into segments so that the loading within each segment is continuous. Thus, the endpoints of the segments are discontinuities of loadings, including concentrated loads or forces and couples. So class, for example, no, for this beam, okay, so class, for this beam, no, we are going to divide this, no, into segments. Okay, so class, we will depend, no, the segment here, class, no, on the loadings. Okay, so let's say, class, we have here this segment AB. Okay, since here at point A, this load starts, no? So this load starts here at point A, and this varying load ends, no? Here at point B. So this will be one segment. Okay, so the endpoints, class, of this segment AB will be the discontinuities, okay, or the discontinuity, okay, of this varying load. Okay, so this varying load, class, this starts again at point A and end here at point B. So this is one segment. Okay, and from point B, class, no, so we will have another segment here from point B to this point, okay, which is point C. So class, here at point C, there will be a reaction force here, right, since we have a support here. So this will be another segment. So this will be segment BC. Okay, and also, class, no, from point C, we will have another segment. So that another segment will be segment CD. Okay. Okay, so that's the first step, how we have to divide, okay, the beam into segments depending on its load. Okay, so again, we will have here segment AB, segment BC, and segment CD. Okay. So class, section the beam at each distance x. So for every segment, class, we are going to section a beam or the segment of that beam. Okay, so let's say, class, for this segment AB, we are going to section this segment, class. Okay, so we are going to cut a section here, no, somewhere here, no, at this segment. Okay, and also class, for let's say for segment BC, we're also going to cut a section here. No? So, also for segment CD, we're going to cut a section here. Okay, so we have to section the beam segment at each distance x and draw the free body diagram of one of the segments. Okay, so let's say class for segment AB, let's say we cut the section here at distance x sub 1, no, from the left. Okay, so um, class, no, we are going to consider, no, it can either be this left segment, okay, or this right segment. Okay, so class, in this case, it will be easier if we just consider this left segment of the beam. Okay, so we are going to consider this left segment. Okay, and from here, class, at this section where we cut this beam, there will be internal shear force and internal moment, right? Okay, so be sure, class, that the shear and moment are shown acting in their positive sense in accordance with the sign convention given in figure 6.3. Okay, so again, for shear, no, so it should cause the beam segment to rotate clockwise, so that's our positive assumption. And for moment, it should cause, no, that beam segment to be bent concave upward, right? Okay, so also class, no, for let's say for this segment, BC, if we cut this segment BC, no, at this section, distance x sub 2 from the left, okay, so class, we can consider this left segment or this right segment, no, so it depends, class, no, if what will be easier, no. Okay, so let's say in this case we consider this this left segment. Okay, and class, here at this cut section, there will be internal shear force and internal moment, right? And also here, class, no, let's say for segment CD, we will cut a section here, no, let's say that is a section x sub 3 or distance x sub 3 from the left. Okay, so here, class, no, we can consider either this right segment or this left segment. Okay, so class, if you are going to consider this right segment, so this distance will be the length of this beam minus x sub 3. Okay, since we are going to consider this. So class, for ano lang, no, for consistency here, class, no, we are going to always measure the distance x from the left side of the beam. Okay. Okay. So after that, class, no, the shear is obtained by summing forces perpendicular to the beam's axis. Okay, so we are going to use equilibrium equation here, class, to solve for the shear. Okay, so class, let's say here, no, for segment AB, we cut a section x sub 1 distance from the left. So we consider, let's say, this left segment. So we are going to solve, okay, the internal shear force here using equilibrium equation. And that will be summation of forces vertical, right? And plus that equation will be in terms of x. Okay, so that equation, class, okay, that will be the shear equation. Okay, and also, class, for moment, okay, so let's say for this segment pa din, class, okay, there will be an internal moment here, class, no? So we are going to solve that internal moment. Okay, so that that internal moment, class, it can be solved using equilibrium equation for moment. Okay, so here, class, no, we are going to take moment always, no, at the section, no, where we ano, no, cut the beam. Okay, so that's the axis, or the axis of moment always. Okay, for summing up moment. Okay, so the reason for that is to eliminate the shear force V, which also acts at that section. So it will be cancelled since it's acting at that section. Okay, so class, the moment equation here, class, will also be in terms of x sub 1. Okay, so that equation, class, no, that will be the moment equation. Okay. Okay, so class, after we establish the shear equation and the moment equation, okay, so we are going to use those equations, no, to plot the shear and moment, no, to create the shear and moment diagram. Okay, so class, that will be our first solution. Okay, so we are going to use the shear and moment equations. Okay, so we are going to plot the shear diagram. Okay, so that will be the shear versus the x-axis, no, and the moment diagram. Okay, so that will also be the moment versus the x-axis. Okay, so we will have the x-axis here, class, and then the y-axis, that will be for the shear and for the moment. Okay, so class, shear and moment, they will be platted, okay, separately. Okay, so if numerical values of the functions describing shear and moment are positive, the values are plotted above the x-axis. So we are going to show that, no, later on in our example. Whereas if negative values, no, they will be plotted below the x-axis. Okay. So generally, class, no, it is convenient to show the shear and moment diagrams below the free body diagram of the beam. Okay. So class, we will also have a solution 2, no, for drawing the shear and moment diagram. Okay. But we are going to discuss that in our next discussions. Okay. Okay, so class, for drawing the shear force and bending moment diagram, this table, this will be useful, class, no, in relating loads, applied loads, shear, and moment. Okay, so as you can see here, class, let's say for an applied couple. So this is an applied couple. Okay, so let's say this is the loading of this beam. Okay, so class, if you are going to draw its shear, so its shear will just be like a rectangle, no? Okay, so this will be like a rectangle. And if you are going to draw its moment, class, it will be like, ano lang, no? It's just a triangle. No, there are two triangles here, class. No, also, class, for beams having concentrated load, no, as an applied load. Okay, so its shear also, class, will just be a rectangle. Okay, and for its moment, it will also just be a triangle. Okay, and also, class, if the loading, class, will be uniform loading, okay, so its shear, class, will be triangle. Okay, and its moment will be parabolic. Parabolic, class, meaning to say it will be its equation will be second degree, no, or um, since our equation, class, it will be expressed in x, no, in variable x. So if the equation is or has a degree of let's say 2, or that's the highest exponent, no, of the equation, so that is parabolic. Okay, so also, class, here, oh, for this point load, okay, or concentrated load, no, so its shear will be rectangles, no, and its moment will be triangles. Okay, so also here, this is uniform loading. So for uniform loading, its shear will just be triangle, and its moment will just be parabolic. And plus, for cases that the applied loading is triangular loading or varying load, okay, so its shear will be parabolic. Okay, so this will be second degree curve since the highest exponent for the equation or function will be 2. Okay, and its moment, class, will be cubic. Okay, so it will already it is already third degree. So meaning to say the highest exponent in the equation, class, for moment, okay, is 3, no? Okay. So take note, class, no, of these relationships, no, of loads, shear, and moment. Okay, so class, just to summarize, no, the sequence of the geometry of the relationship of loadings, shear, and moment, now we can take note of this. Okay, so class, if you have a concentrated load, okay, so automatically, class, no, its shear will be rectangle. Okay, and its moment, class, will be triangle. Okay, but if your loading class is like, let's say, a rectangular load or a uniform distributed load, so class its shear will be triangle and its moment will be parabolic. Okay? Let's say naman class that you have a triangular loading. No, so that is a uniformly varying load. Okay, so if your loading is a triangular load class, its shear will automatically be a parabolic and its moment will be cubic. Okay, so this will be the sequence of the geometry, again, of loadings, shear, and moment. And also, class, we can use these rules, no, in drawing the shear and moment, no. So, class, let's say we have here these loads. Okay, so for these loads, they are all negative since they are all directed downward, right? So, class, for this load, so this is negative constant. So, this is constant negative, no? Since this is uniformly distributed, no? Okay, so class for these types of loads, okay, so its shear, okay, it will always be sloping down. Okay, so take note, class, that for rectangular loads, okay, its shear will be triangle. Okay, and the triangle here, class, will always be sloping down. Okay, it will be here at this point, no, downward to the right. Okay, it will always be sloping down. And also, class, no, for um let's say for negative increasing. So this is negative class, and the negative this negative loading class, this is increasing, right? No, so from this point to the right, no, so it is negative increasing. Okay, so for this loadings class, no, if this is the loading, its shear, it will be concave down. Okay, take note of this class, it will be concave down. Okay, it will be concave down. And also, class, for loadings that are negative decreasing, so as you can see here, class, no, this is negative loading, no, and this increases, no, as it moves from the left to the right. Okay, so this is negative decreasing. And for loadings that are negative decreasing, its shear class, it will be concave upward. Okay, it will be concave upward, ha? Okay. Also, class, no, we also have this rules. Okay, so class, if your shear, okay, is sloping down, so these are shears that are sloping down. Okay, so this is going down, no, from left to right. So this is sloping down. This is also sloping down. This is also sloping down. Okay, for this shears class, okay, automatically, class, its moment will be concave down. Okay, it will be concave downward, either concave downward this way or concave downward this way. Concave downward, ha? This is concave downward. Okay, so class, on the other hand, class, if your shear is sloping up, so it is going up, no, from left to right. Okay, so this is sloping up, this is sloping up, this is also sloping up. So automatically, class, its moment, okay, it will always be concave upward. So as you can see here, this is concave upward, and also this is concave upward. So, okay. So, class, it's actually easy. No, it will be easier to remember this. No, for example, for this shear. Okay, so since the shear is sloping down, it will be a sad moment, right? So if it is a sad moment, so therefore the concavity class of this moment, it should be downward. No, so this is like ano, no, a sad smile or sad smiley. No, so this is sad. No, so if the shear is sloping down, the moment will be sad. On the other hand, class, if the shear, if it's sloping upward, okay, so the moment will be a happy moment. No, so it will smile. So this is like a smile, right? Also this, it's like a smile. Okay, so that's how I remember it, class, actually. And also for this, no, so if the loadings class is downward, no, it will always be ano, sloping down. Okay. Okay. Okay, so let's start solving sample problems here. Okay, for sample problem number 1, establish the shear and moment equations for the beam shown in the figure. Draw also the shear and moment diagram. Okay, so for this beam class, so this beam is simply supported since it has a hinge or pin support here at one end, and at the other end, no, this has a roller support. Okay, so this beam class has a length L, okay, and it carries this uniformly distributed load with an intensity of W. Okay, so for this beam class, now we are going to establish the shear and moment equations, and we are also going to draw the shear and moment diagram. Okay, so for this problem class, to establish the shear and moment equations and draw the shear and moment diagram, okay, we are going to do first, no, our first step. No, so our first step here, class, we have to compute the support reactions. Okay, so to do so, we have to draw the free body diagram of the entire beam. So for this beam class, no, so this will be the free body diagram. Here, at this end class, it is hinge supported. So supposedly class, there will be two reactions here, one horizontal reaction and one vertical reaction. But as you can see here, class, no, there is no horizontal loadings here, class, right? There's no applied horizontal loading in the beam. So therefore, there will be no horizontal reaction. So we will only have here a vertical reaction at the hinge support. And also, class, for the roller support, so we know that it only has one reaction, and that will be a reaction normal or perpendicular to the surface where the roller um, is leaning. No? So in this case, this is a horizontal surface, class. So the reaction here, class, will be perpendicular to this horizontal surface. So we will just have a vertical reaction here also. Okay, so class, we are going to solve this reaction forces, ha. So we are going to use statics here, no? So from your from equilibrium equations, class, no, we can solve for the reactions here at the left and here at the right. Okay, so we can sum up moment, no? Let's say here at this point. Okay, so that will be summation of moment at this point, class. So this will be equal to 0, and we will assume positive moments, no, for clockwise rotation. Okay, so here, class, now we can solve for R sub L. Okay. Okay, so from here, class, the forces that will have moment at this point, okay, so will be um, this reaction. This is R sub L. Okay, and then, class, its moment arm will be L, right? So this is the perpendicular distance or its moment arm from the center of moment, which is at this point. Okay, so that will be its moment, and its rotation, class, about this point, okay, it will be clockwise. So it will be positive here in our summation. Okay, and also, class, this distributed load with an intensity of W, it will also have a moment at this point. So in this case, class, no, to solve for the moment of this distributed load. So this is a rectangular loading, no? So we have to solve for its equivalent point load. Okay, so its equivalent point load will be the area of this rectangular load. So that will just be the height, which is W, and then its base is L. So this will be the magnitude now of the equivalent point load, no, of this rectangular load. So that will be WL. So this point load, class, it will be located, no, here at the centroid, no, or center of this of this loading. So let's say here, no, so this is applied, this point load, class, will be applied L over 2, no, either from the left or from the right. Okay, so this will be here. Okay, and its moment, class, about point O, its moment arm will be L over 2, no. So that's why we multiply it here by L over 2. Okay, so class, the moment of the equivalent point load class about this point, okay, it will be rotated this way. So this is counterclockwise. That's why it's negative here. So this will be equal to 0. Okay, so solving for our sub L class, so we transpose this, no, to the other side, so it will become positive, and this will become WL squared over 2. Okay, and solving for R sub L, so that is the reaction at the left support, no? So we will just divide both sides by L, okay, to cancel this L here. Okay, so dividing both sides by L, so RL now will be equal to WL over 2. So the L here will be, ano, no, L squared, it will become L, and then the L, no, in the denominator, it will be cancelled. Okay, so this will now be the reaction here, no, at this point. Okay, so this is equal to WL over 2. Okay, so class, to solve naman, no, for the reaction here at the right support, okay, so we can now just use summation of forces vertical here. No, but we can also take moment here at this point, no, to solve for the reaction here. Okay, but in this case, we're just going to sum up forces vertical and upward forces that will be assumed as positive. So in this case, class, this will be RL. Okay, so this is positive since this is upward. And then plus the equivalent point load or concentrated load of this rectangular load is just the area. Okay, so that will just be WL. So it will be downward. That's why it's negative here. And the reaction here, class, no, it is upward. So it will also be positive here in our summation. So this will be plus R sub R. Okay, so we can substitute the value of the RL that we solve here. Okay, so substituting that value here, so this will become WL over 2 minus WL plus reaction at the right support. No? So this will be equal to 0. So solving for the reaction at the right support, it will just be WL over 2 minus W minus WL. Okay, so in this case, class, no, so WL over 2 minus WL is actually negative WL over 2, right? So, transposing that to the other side, it will become positive. So, the reaction, class, at the right support will be WL over 2 also. Okay, so class, this is actually of use, no? So, since our loading here is constant or uniformly distributed, okay, and the reactions are here and here. Okay, so obviously, class, these supports, okay, they or the loading, this loading class, it will just be divided into two supports, right? So it will just be this support, these reactions at the left and the right, they will just be equal. They will just be both WL over 2. Okay, so class, after we determine the support reactions, we will now proceed to our next step. So that will be establishing the shear and moment equations. Okay, so establishing the shear and moment equations, we have to divide first, no, the beams into segments. But in this case, class, since the loading here in our beam, no, so it starts at this point and end at this point. So this will be one segment. No, so our beam will just be one segment. So meaning to say, class, there will only be one shear equation here and one moment equation here since we only have one segment. Okay, so class, we are going to section this segment, no, or this beam, no, we are going to cut a section here. No, so anywhere actually, no, anywhere at this segment, we can cut a section. Okay, so we are going to cut that section, cut a section, no, in this beam, X distance from the left. Okay, so this X distance, this can be any, ano, no, any distance. Okay, so this will be a variable X. Okay, so class here, no, if we cut a section anywhere in this beam, okay, so let's say we cut it here. Okay, so class, we are going to consider either this left segment or this right segment. But in this case, class, no, we are going to consider the left segment. Okay, so this will be the left segment, class, of the cut section. Okay, so class, here we are going to um, of course consider here the loading applied at this segment that we consider. So there will be still an there will be uniformly distributed load here, no? So this is the applied loading here. Okay, and we will also include here the reaction at the left support, which is WL over 2. Right? So, from here, class, no, at this cut section, we are going to show here, no, the internal loadings, which are the internal shear force and the internal moment. So, again, class, our um, uh, the way we are going to draw, no, this internal shear force and internal moment will be according to the positive sign convention, ha. So for the shear force V, it should be drawn downward, no. So since this is the positive assumption, right, for shear, it should cause this segment of the beam not to rotate clockwise. So this will rotate clockwise, no, this shear force V. So that will be our positive assumption. And for moment, class, this moment, it should cause the segment of the beam not to be bent concave upward. So this will really cause the beam to bend, okay, concave upward. Okay, so this will be ano ha, this will be drawn this way. Okay, so this is the moment and this is the shear. Now, class, no, after we draw this free body diagram, class, we are going to solve for shear. No, so to solve for shear, class, no, we can use equilibrium equation. So that will be summation of forces vertical. Okay, so in this case, class, for this uniform loading, okay, so we will convert it into its equivalent point load. Okay, so as you can see here, class, this rectangular loading or uniformly distributed loading, class. So this is this still has an intensity of W, right? Even if we cut this here, so this is still an intensity of W, no. So class, it's equivalent point load, no, for this rectangular loading at this segment. So its height will be the intensity W and its base will be X. So solving for its point load, that will be just solving its area. So that will just be base times height, or W times X. No, so this will be its equivalent point load. Okay, so this point load, class, now this equivalent point load, so this will be applied at the center. No, so this will be x over 2 either from the right or from the left. So this is also x over 2 from the left. Okay, so class, again, for the shear equation, okay, or to solve for shear, we are going to we are going to use summation of forces vertical here equal to 0. So for upward forces, that will be positive. Okay, so the vertical forces here will be this force, and the shear force, right? So this will be, for WL over 2, it will be positive since it is upward. And for this WX, it will be negative since this is downward. And for the shear force V, so this will be negative since this is directed downward. No? So this will be equal to 0. And solving for V, class, so this will be, we just transpose this negative B, no, to the other side, so it will become positive. So this will be equal to WL over 2 minus WX. Okay, so we can factor out W here, right? So this will become V is equal to W times quantity L over 2 minus X. Okay, so in this case, class, so this will now be the shear equation. Okay, so you can already box this. So this shear equation, class, okay, so we can use this shear equation for this segment. No, so class, if you are going to cut a section anywhere, no, at the segment of this beam, Okay, for every distance x class, no, we can substitute that here. Okay, and at that section, distance x from the left class, no, we can know the internal shear force acting at that section. Okay, also class, let's say here at this section, so the distance x will be the distance from the left. Okay, so um, we can just substitute that distance x from the left in this equation and solve for the shear force, internal shear force acting at that section. Okay, so that's the purpose of our equations here. So this will be for the shear equation. Now, class, for the moment equation, we are going to use summation of moments here. Okay, so again, class, we are going to sum up moment or take moment always, no, at the cut section. Okay, so the reason for that is to cancel this unknown shear force V or internal shear force V. Okay, since it will act at this section, class, no, so this will be canceled, no. So that's the reason why we are going to take moment always at this section. So taking moment, class, no, at this section, okay, so this WL over 2 and WX, they will both have moment, no, at this axis or section, no, okay, or point rather. Okay, so in this case, class, no, summing up moment, okay, so this will be equal to 0, and our assumption for positive rotation here will be clockwise. Okay, so in this case, class, the moment of WL over 2 will be WL over 2 times its moment arm, which is x. No, so this will be WL over 2 times x. Okay, and its rotation, class, it will be clockwise, right, about this point. Okay, so that's why it's positive here. Now, class, for this WX, its moment about this point will be WX times its moment arm, which is x over 2. Okay, so that is the moment. And class, its rotation about this point will be counterclockwise. That's why it's negative here. And class, for the internal moment here, so we assume it as directed this way. Okay, so this is actually counterclockwise, right? So this is counterclockwise, so it will be negative here in our summation, no? Okay, equal to 0. So solving for m, class, so we just transpose this negative m to the other side. So this will become m is equal to WL over 2 times x, or WL x over 2 minus WX squared over 2. And we can factor out WX over 2. So factoring out WX over 2, it will become WX over 2 times L minus X. Okay, so class, this equation now, okay, this equation now, class, this will be the moment equation. Okay, so for any distance x, no, from the left side of this beam, okay, let's say at this section, no, for the distance x here, for this section, class, no, we can substitute that distance x, no, at the variables x here, and then solve for the internal moment acting at that section. Okay, so even if we cut section here, class, so there will also be a distance x. So that distance x we can substitute here and then solve for the internal moment acting at this section. Okay. Okay, so for the shear and moment diagram, class, it can be obtained by plotting the equations for shear and moment. Okay, so we are going to use the shear and moment equations that we just derived, no, from the previous slide. Okay, so these equations, class, no, they can be applied, no, at any distance x, no, so from 0 to L, since that is the length of the segment of the beam that we considered. Okay, so class, for the shear, okay, so this is the equation for shear. So here, class, no, we are going to substitute values of x, no, to graph, no, the shear. Okay, so class, we are going to let's say for distance x equal to 0, so that will be at the leftmost part, no, of the beam. Okay, so the shear there class, no, at x equal to 0 will be, okay, so we will just substitute class this value of x here, no, at the variable x. So this x will be 0. And solving for shear class, so this will just be WL over 2. And take note class that this value is just actually the value of the reaction at the left support, right? So that will just be equal, the shear will just be equal to that reaction force. Okay, so this will be the shear force class at x is equal to 0. And also class, let's determine the shear force at x is equal to L. Okay, so for x is equal to L, we'll just substitute this L to the value of x here in our shear equation. Okay, so this will become W quantity or times quantity L over 2 minus L. So we know that L over 2 minus L, this is negative L over 2, right? So class, the shear, no, at distance x is equal to L class, it will be negative WL over 2. Okay, so class, we can graph, no, these values. Okay, so class, for the shear diagram, we are going to draw this, no, right below, no, the free body diagram of the beam. Okay, so class, at x is equal to 0, so x is equal to 0. So this is our x-axis, ha. Okay, so this is our x-axis. And the y-axis here, class, okay, so it will serve, no, as the, or this is where we're going to plot the values of the shear or the shear force. Okay, so at x is equal to 0, class, okay, so we already computed the value of shear if x is equal to 0. And the shear here, class, is WL over 2. So, class, the value of shear here is positive. So, meaning to say, we are going to plot this value of shear, no, above the x-axis since it is positive. So, WL over 2, class, it will be plotted here, no, above the x-axis. And also, class, for the shear force at distance x is equal to L. So, distance x is equal to L. So, that point is here. Okay, so at this distance, class, okay, the shear force here, class, is negative WL over 2. So, since this is negative, class, it will be plotted below the x-axis. So, it will be plotted here. So, from the points that we have here, class, so we have your point here, okay, and point here. So, we are going to connect these points. Okay, and class, remember that for rectangular loadings, each shear will be triangle. So, we will connect these 2 points, no, by this straight line. Okay, so this will just be a straight line, ha, since it should create triangles, right? Since the loading here, class, is rectangle. Okay, so these 2 points, the point here and point here will be connected by this straight line. Okay, so there will be a form triangles here, class, right? Okay, so this triangle and this triangle. Okay, so class, this will now be the shear diagram. Okay, shear diagram of this beam. Okay, and class, this distance, L over 2, this is actually unknown yet. We don't know yet, no, if what is this distance from this point up to this point. Okay, so class, we can determine this distance, okay, by noticing here, class, that at this point, no, so at this point, so this is distance x from the left. Okay, so at this point, class, the shear here is 0. So meaning to say, we can use this equation, okay, to solve for this distance x by substituting 0 for this v, since the shear here nga, class, is 0, okay, at distance x. So substituting that, class, okay, 0 for the shear force here. So this will be 0 is equal to W times L over 2 minus X. And solving for X here, class. So, class, we can divide both sides by W first. Okay, so that this W will be cancelled. So, 0 over W, that will just be 0. So, this will now become X. So, we transpose it to the other side. So, it will become positive. So, this will now become X is equal to L over 2. That's why here, class, no, so this distance is just L over 2. And actually, class, this is just obvious naman, okay, that it should really be at the midspan. No, the shear force here, class, no, at the point, at the midspan of the beam, it should be 0. Okay, or it will be 0. Okay, so that will be, this will now be, class, the shear diagram of this beam. Okay. So, class, we will also plot here, no, the moment diagram. So, we are going to use the equation for moment equation. Okay, so this is our the equation that we derive, no, for moment. Okay, so class, here we are going to determine then, no, the values of moment, no, in every distance x. Okay, so we will start with distance x is equal to 0. So the moment, class, at distance x equal to 0, so we substitute 0 to all the variables x here. So obviously, class, no, the moment, no, at x is equal to 0 will just be 0. Okay, so the moment, class, here, no, at this point, it will be 0. Why? Because, class, there's no really moment here at this point. Right? There's no moment here at the leftmost part of the beam. So the moment here, class, will be 0. Same with, actually, with the other end. No, if x is equal to L, so later on I will show you that, no, that the moment here, if x equal to L, will just be 0 also. And, class, here, no, if you are going to plot, class, the moment diagram, we will depend that, no, to the shear diagram. Okay, so in this case, class, for our shear diagram, so our shear diagram here, class, this is divided into two segments. So we have here this segment and this segment. Okay, so, class, we are going to determine, okay, the moment, no, at this point. Okay, so for this segment, class, at this endpoint, okay, so we are going to determine also its moment. Okay, at in this point nga, no. So, class, at this point, we know that this is distance x is equal to L over 2. So we are going to determine the moment at that distance x. Okay, so x equal to L over 2, we will substitute this L over 2, no, to all the variables x in our moment equation. So, this will become W times L over 2 times quantity L minus L over 2. So, simplifying this, class, so this will become WL over 2 times 2. So, that will be WL over 4. And then this one, L minus L over 2. So, this is L over 2, right? Okay, so simplifying this further, this will become WL squared over 8. Okay, so this is the moment, class, no, here at this point. Okay, and also, class, for x is equal to L, okay, for x equal to L, we will just substitute this value, okay, to all the variables x. Okay, so this will now become W times L over 2 times L minus L. Okay, so L minus L, that will just be 0, right? So, the moment, again, class, no, for distance x equal to L will just be 0. So, we are going to plot this, class, no, in the moment diagram. So, this will be our moment diagram. Okay, so this will be drawn, no, before or below, no, below the shear diagram. Okay, so, class, this will be the x-axis, and the y-axis here, class, will be for the values of moment. So, at x is equal to 0, which is at this point, so the moment, class, is 0. So, it will be 0 here. Okay, and at this point, class, so this is L over 2. Okay, for x equal to L over 2, class, the moment is WL squared over 8. So, WL squared over 8, let's say that is at this point. Okay, and then for x equal to L, class, the moment is 0. That's why it will be 0 here. Okay, so we are going to connect those points, class. This point, this point, and this point. And class, in connecting those points, we are going to apply here, no, the rules that we talked about in the previous slide. So class, for shear, okay, that is sloping downward. Okay, so this is sloping downward. Okay, so class, the moment should be, so for this segment, okay, so the shear here, class, is sloping down, right? So if it is sloping down, so the way that we are going to connect the point here to this point, it should be, the curve here should be concave downward, since the shear here, class, is sloping down. Right? And class, this is triangle. No, the shear is triangle. Therefore, the moment, class, will be parabolic. Right? That's what we discussed, no, in the previous slide. So again, class, since the shear here is sloping down, therefore the curve here should be concave downward. Okay, from this point to this point. That's why it is concave downward. Okay, and also class, from this segment, from this point to this point, the shear also here, class, is sloping down. So meaning to say, class, okay, the curve that will connect the point here and this point, it should also it should be concave downward, right? That's our rule. That's why it's concave downward here. Okay, so class, this will now be our moment diagram. Okay, and as you can see here, class, okay, so this will be the maximum moment, WL squared over 8. No, and take note, class, that this maximum moment, okay, it occurs at the point of zero shear, right? So this is the point of zero shear. So this is where the maximum moment occurs. Okay, so this will now be the shear and moment diagrams, class, ha? Okay. Okay, for sample problem number 2, we are going to establish the shear and moment equations for the beam shown. And we are also going to draw the shear and moment diagram. So we have here a cantilever beam here. Okay, so this is fixed supported at one end and free at the other end. So this beam, class, has length L. Okay, and this beam carries this load. So this load, class, this is um, a varying distributed load, right? So this is a triangular load. Okay, so class, at this point, class, okay, so this load, this has an intensity of W sub O. So at this point, obviously, its intensity will is 0. No, the intensity of this loading here is 0, and at this point, this is W sub O. So let's solve this problem, class. Okay, so for this problem, class, okay, again, we are going to start with the computation, class, no, of the reaction forces, no, here at the support. So we are going to draw here the free body diagram. Okay, so class, here, no, for fixed support, we know that there will be 3 reactions, right? So there will be horizontal reaction, there will be vertical reaction, and a reaction moment, or a moment reaction. Okay, so in this case, class, there will be no horizontal reaction since there is no horizontal applied loading. No, so we will only have here one vertical reaction, and we will name that as R sub L. Okay, and we will also have here a moment reaction, and let's name it as M sub L. Okay, so class, for this loading, so this is a triangular loading, we can compute its equivalent point load. So its equivalent point load will just be um, the area, no, of the triangle, which is 1/2 base times height. So that will just be 1/2 times W sub O times L. right? That's why this is W sub O L over 2. So this is the magnitude, no, of the equivalent point load. And this equivalent point load or concentrated load class, okay, so this will be located 2/3 L, no, from the point or from the tip of this triangle. So this is 2/3 L, okay, from here. So if it's from the right class, okay, so this is 1/3 L. If we measure the distance from this side, okay, so this is 1/3 L. But from here to the location of the point load, this is 2/3 L. Okay, so from here, class, no, we can now solve for the vertical reaction here, no, using summation of forces vertical. So this will be summation of forces vertical is equal to 0, positive for upward forces. Okay, so R sub L, so we assume it as upward, so this will be positive here. And then for this equivalent concentrated load, so this is downward, so this will be negative here. So this will be negative W sub O L over 2. So this will be equal to 0. So we can directly solve for R sub L here. So R sub L here, class, this is equal to W sub O times L over 2. Okay, so that is the value of the support or the vertical reaction here. And also, class, for this moment reaction, we can solve this by summing up moment, okay, at this point. So summing up moment at this point so that R sub L will just be cancelled. Okay, so this will be equal to 0 and clockwise rotations will be positive. So in this case, class, this moment reaction, this is this is counterclockwise. So it will be negative in our summation. Okay, so that's why it's negative here. And then the moment of this concentrated load about this point, okay, that will be W sub O L over 2 times its moment arm, which is 2/3 L. Okay, so its rotation, class, about this point will be clockwise. That's why it's positive here. So simplifying this, class, okay, so this will become, these two will be cancelled, right? This will be cancelled. So this will become 1/3 W sub O, and then L times L, that is L squared. So this will become, for ML or M sub L, okay, so this is the moment reaction. This will be equal to W sub O L squared over 3. So these are now the reactions, no, here at the fixed support. Okay, so after this, class, no, we can now establish, okay, the shear and moment equations. Okay, so we are going to cut the segment of this beam. Okay, at this, in this case, class, no, so we will only have one segment since the loading starts here and ends here. So this entire beam will just be one segment. Okay, so we will cut, no, a section, no, or any section in this beam. Okay, so we will cut any distance x, no, from the left. Okay, so we are going to cut this beam, no, let's say here. Okay, and we can either consider this left segment or right segment. But in this case, class, we will consider this left segment, ha? Okay, so considering the left segment, class, this will be the free body diagram. Okay, and this left segment, class, of course, there will still be applied loading here. And the applied loading here will still be a triangular loading since if we cut this here, no, so the loading remains triangular. Okay, and let's say, class, that the intensity of this triangular loading at this segment, okay, so this intensity, let's say this is W. Okay, so this is different from W sub O. Okay, since this is the triangular loading at the cut section. Okay, so we will just name this intensity as W, ha? Okay, so also, class, we will include here the reactions that we solve here, no? Okay, so the vertical reaction here is W sub O times L over 2. Okay, and the moment reaction here is W sub O L squared over 3. Okay, so we will include that here. And class, for this triangular loading, if you're going to compute its equivalent concentrated or point load, so that will just be the area, that will be 1/2 W times X. So this is distance X, ha, this segment, this is distance X, okay, from the left, Okay, so class, here, no, at the cut section, we are going to um, show here, no, the internal force and moment. Okay, so this will be the internal force. This is the internal shear force. So again, we will assume the direction here, no, the direction of the shear for positive shear. And the positive shear here, class, is the shear that will cause this segment to rotate clockwise. Okay, so that's why we assume it directed this way. And also for the moment, we will assume the direction of the moment that will tend this beam segment, no, to bend concave upward. So we will assume it directed this way, no, the moment. Okay, so class, from this free body diagram, okay, we can now establish the shear equation, no, by summing up forces vertical. Okay, so summing up forces vertical here, class. But class, here pala, no, we are going to determine first, no, the intensity W. No, so we can determine the value of this intensity W, no, by considering the proportion of the triangles here. So since we cut this loading, no, at this section, okay, so this triangle, it will just be similar to this larger triangle. So we can use proportion here. Okay, so that will just be the height over the base of the triangle, of this smaller triangle, and that will just be equal to the height over the base of the larger triangle. So in this case, for the smaller triangle, the height is W and the base is X. So that will be equal to the height of the larger triangle, which is W sub O, and the base of over the base of the larger triangle, which is L. Okay, so from here, solving for W, so W will just be, we just cross multiply this, no? Okay, so this will become W sub O times X over L. So this will now be the value, no, of the intensity W. So from here, class, we are going to use this. No, we are going to substitute this W to this value. Okay, so from here, class, okay, also class, no, take note that this equivalent concentrated load, so this is 1/3 L from the left, no, from this tip of the triangle, this is 1/3 L, or 2/3 L rather, or 2/3 X, since the distance here is X. Okay, so from here, from this point up to the location of the point load, this is 2/3 X. But if you are going to measure that from here to here, this is 1/3 X. Okay, so from here, class, again, we are going to establish the shear equation, no, by using summation of forces vertical. Okay, so class, the equations that we're going to establish here, this will be applicable, no, for any distance x from 0 to L. Okay, so summing up forces vertical here, class, no, from this free body diagram. So this will just be W sub O L over 2. So this is upward, so it is positive here. And then for the equivalent point load, this is 1/2 W. The value of W is W sub O times X over L. So we will substitute that here, no? And then this is downward, so it is negative here. And then our shear force here is downward, so it will be negative here. Okay, so we are going to substitute the W that we solved from here. So simplifying this class, no, so this will become, for this term, no, so this will become 1/2 W sub O X squared over L, right? So solving for V here, class, so we will transpose this negative V to the other side, so it will become positive. So V now, it will be equal to W sub O times L over 2 minus W sub O X squared over 2L. Okay, so class, from here, no, we can factor out W sub O over 2, right? So we can factor that out, and then it will become W sub O over 2 times L minus x squared over L. So this will now be the shear equation. Okay, so you can now box that, no, since we are solving for that shear equation. Now, for the moment equation, we are going to take moment here, no? So, class, again, we are going to take moment, no, at the section, no, or at the cut section, okay, to cancel the internal shear force V. Okay, so taking moment, class, at this point, no, of the cut section, okay, so this will be equal to 0, and then our assumption will be clockwise, rotation will be positive. Okay, so class, of course, we will include this moment reaction. So this moment reaction, class, this is W sub O L squared over 3, and this is counterclockwise. No? So it will be negative here in our summation. And then for this reaction force, no, so its moment about this point, so that will be W sub OL over 2 times its moment arm, which is distance x. No, and its rotation will be clockwise. That's why it's positive here. Okay. Now, for this equivalent point load, so for this equivalent point load, this is 1/2. Its moment, no, about this point, so this will be 1/2 times W, which is W sub O x over L, and then times x, and then its moment arm, class, will be 1/3 x. That's why it's multiplied by 1/3 x here. And its rotation, class, about this point will be counterclockwise. That's why it's negative here. Okay, and class, for the internal moment that we are solving here, so this is counterclockwise. So it will be negative here. Okay, so solving for m here, class, now we are going to transpose, not this negative m to the other side, so it will become positive. So simplifying this, so this will become, so this will still be negative W sub O L squared over 3. And then for this will become W sub O times L times X over 2. Okay, for that term. And then for this term, class, okay, so this will become 1/2 times 1/3, that is 1 over 6. So this is negative here. Okay, and then we have here x times x times x, so it will become x cubed, no? And then W sub O over L. Okay, so from here, class, we can simplify this further by factoring out W sub O, okay, over, I think we can also factor out x, no, no, there's no x. So W sub O over 6, we are going to factor that out. Okay, so this will become W sub O over 6 times negative 2L squared. So this negative 2L squared times WO over 6, so this will be equivalent to this. Okay, so, and then plus 3LX. So 3LX times WO over 6, that will be equivalent to this. Okay, and then for negative x cubed over L times WO over 6, so that will be equivalent here. Okay, so class, this will now become the moment equation. Okay. Okay, now for the shear and moment diagram, so it can be obtained by plotting the shear and moment equations, no, that we derived from the previous slide. Okay, for the shear equation, class, okay, so we are going to use this shear equation. So this shear equation, class, no, it can be applicable at any distance x from 0 to L. Okay, so if x is equal to 0, class, okay, so we are going to solve here, no, the corresponding shear or shear force, no, at x is equal to 0. So we're just going to substitute this value of x, no, to the variable x in this shear equation. Okay, so substituting that here, so this will become 0 squared. No, so what happens is here is that this will be 0, and then W sub O over 2, it will be multiplied by L. So shear here will be equal to W sub O times L over 2. Now, for the shear at x is equal to L, okay, so we will just substitute this value to the variable x here. So this will become L squared, no, over L. L squared over L, that is actually L. No, L will be cancelled and L squared will become just L. Okay, so L minus L class will be 0, right? So class 0 times W sub O over 2. So the shear class at distance x equal to L, class the shear is 0. Okay, so if we are going to plot this class, no, in the shear diagram, okay, so this will be our x-axis. Okay, so class, the shear diagram, it will be drawn, no, below the free body diagram of the beam. Okay, so class, for x is equal to 0, so x equal to 0 will be at this point. Okay, the shear here, class, is W sub O times L over 2. So this is positive, so it will be plotted above the x-axis. So this will be the shear force here. Again, this is W sub O times L over 2. And class, take note again that this shear here, this will just be equal to the um, reaction force here, no, at this point. So the reaction force here is W sub OL over 2 also, right? Okay, so that will be equal to the shear at this point. Okay, and also class, for x equal to L, so x equal to L will be at this point. Okay, the shear here, class, is 0. Okay, so we have here 2 points, no? So we have here the shear at this point and the shear at this point. So in this case, class, we are going to connect this point, these 2 points, the point here and the point here. So class, from the loading, okay, so as you can see here, the loading here is negative increasing. No, so if the load is negative increasing, class, so the curve, okay, that will connect these 2 points, it should be concave downward. No, so that is that is mentioned in our discussion. Okay, so it will, the curve here will be concave downward. And class, since the loading here is a triangle, of course, the shear, it should be parabolic. So this is parabolic, class. No, so based on the shear equation, class. Here, class, no, the highest exponent of the variable x is 2. No, so this is x squared. So meaning to say, class, this is parabolic. No, this equation is parabolic. So this curve, okay, so this curve, class, no, in the shear diagram, this is parabolic. Okay, so again, this is concave downward, ha. So this is concave downward, concave downward. Okay, since the loading is negative increasing. Okay, so this will now be our shear diagram. Now, for the moment diagram, we are going to use our moment equation. This is our moment equation, class. So this will be applicable, no, at any distance x from 0 to L. Okay, so class, we are going to determine the moments, no, at x is equal to 0 and also for x is equal to L. No, so since the shear here, class, this will just be one segment only, no. Okay, so we are going to solve for the moment at x equal to 0 and moment at x equal to L. So for x is equal to 0, class, so we will substitute 0, no, to all the variables x here. Okay, so for this x, we will substitute 0. For this x cube, we will substitute 0. So this will become 0 cube. So simplifying this, class, this will become 0. This will also become 0. So what will remain here is negative 2L squared. So negative 2L squared times W sub O times 6. So that will be negative 1/3 times W sub O L squared. Now, so this will be the moment, class, no, at x is equal to 0. And realize, class, that this moment is just actually equal to the moment reaction here at this point. So the moment reaction at this point is W sub O times L squared over 3. Right? So, class, here, this moment is counterclockwise. Okay, so this is counterclockwise. And class, for moments that are counterclockwise, okay, so if we are going to plot that, okay, in our shear or in our moment diagram, it will be plotted below, the x-axis, ha. Okay, so that will be negative moment. Okay, so class, also we are going to determine the moment for x is equal to L. Okay, so we are going to substitute L, no, to all the values of x here. So this will become L times L. And then this x cube, it will become L cube. Okay, so simplifying this class, so this will become negative 2L squared plus 3L squared minus L squared. So L cube over L, that will just be L squared, right? So simplifying this class, negative 2L squared plus 3L squared minus L squared, that is actually 0. Right? So that will be 0. So the moment here, class, is 0. Okay, so class, we are going to plot this now, no, in the moment diagram. Okay, so this, the moment diagram, class, so this will be drawn, no, below the shear diagram. Okay, so this will be the x-axis, and the y-axis, class, this will be for the values of the moment. Okay, so class, for x is equal to 0, so this is x is equal, this is the that point, no, for x equal to 0. So the moment here, class, is negative w sub o L squared over 3. So class, this is negative. So this will be plotted below the x-axis. That's why it will be here. Okay, so again, class, this value of moment, no, so this will just be equal to the moment reaction at this point, which is w sub o L squared over 3 counterclockwise. This is counterclockwise, right? Counterclockwise, class. So, class, this moment, this will cause this segment of the beam to be bent, or to be bent concave, concave upward, right? So, this is a negative moment. Okay, so it will uh, bend, no, the beam this way, since the moment is directed this way, no. So this will, no, so this will cause this segment of the beam to bend concave upward. Okay, that's why it's a negative moment. So for negative moment, class, again, this will be plotted below the x-axis. Okay, that's why it's here. Now, class, for the moment at x is equal to L, at this point, the moment, class, is 0. So the moment here, so it will be plotted here, no, at the x-axis mismo. Okay, so class, we are going to connect these 2 points, this point and this point. So we are going to connect this. So the way that we are going this, class, we are going to depend it, no, on the shear. So class, for this shear, as you can see, this is sloping down, right? The shear is sloping down. Right, from the left to the right, this is sloping down. So class, shear that are sloping down, no, for moment, it should be concave downward. That's why we are going to connect the point here and the point here, no, by a curve that is concave downward. Okay, so this is concave. Class, this graph, no, for moment diagram, class, this is cubic, or in third degree, because as you can see in the equation, class, for moment, okay, so this is x cubed. So the highest exponent of variable x here, class, is 3. No, so this is cubic. And so again, this will now be the shear and moment diagram, class, for this problem. Okay, so the continuation of this discussion will be shown in the next video.